So let me share the screen. Is it visible? The whiteboard.
Sir. Yes, sir.
So okay. So in the last class we discussed the basic equations of DC machines. Started with the type of DC machine, that is DC generator and motor. And in generator, you know, the mechanical power is converted to electrical power. And in the motor, the mechanical and the electrical power is converted to the mechanical power. That means in generator we get the some sort of voltage and current in output, and in DC motor we get the mechanical rotation or torque at the output. So both the conversion in generator as well as in the motor takes place in the presence of magnetic field. So that we mentioned at the beginning. Then we started with the basic structure of a DC machine, where there are two poles in the stator. Stator is the static part of the machine which doesn't rotate, and there we have two poles, North Pole and South Pole, and we assume the conductor which is rotating at a certain speed, omega. Then we instead of taking one conductor, we took a coil. Coil is consist of two conductors. If the coil is one turn coil, then it will have two conductors. So this is how the conductor is defined. Okay. So one turn coil means two conductors. That means if the coil is made of 10 turns, then we'll call it two N conductors are there in the coil. So then we discuss the flux distribution, which is very important. I mentioned flux distribution in the air gap, or in the air. If we travel from A to B, B to C, C to D, D to A. So that means if we travel in a circular path near to the whole surface, so then we'll get experience some flux or some magnetic field that we drew in the last class, and it was look like a flat of nature. It's not exactly sinusoidal, but it's if the sinusoidal has its top is flat, then it will be like that. Okay, so the flux distribution, that is the flux with respect to the space angle. This particular distribution, you should remember that this particular distribution will not change with time. As the North Pole and South Pole, as these two poles are fixed in space, so that means this distribution will not vary with time. Neither this distribution nor the flux at any point. So that means flux at any point will not vary with time, but the flux will vary with space angle. Okay. Why it is not varying with time? Because we are applying a DC current in the field circuit. Okay, or we have a permanent magnet field. If the field is permanent magnet, then also this distribution will not change. Or if we apply some current to the field winding, then also what is field winding I will discuss today. And then we define some terms like the phase coil span. Okay, so and the short pitch coil, full pitch coil. So we define those things. If you read this, then you will understand. And the video I have shared and the notes also I have shared. I think you received all this. Then we discussed how the voltage is getting generated in a DC machine, not in a generator, but in a motor all as well. So that means the induced voltage in a DC machine, assuming the flux density space distribution, flux density space distribution, we have assumed purely sinusoidal. So this point you should remember, because the original flux density distribution was not sinusoidal at all, as you have seen in the previous figure. But here we have assumed only sinusoidal part of it. We have not considered any harmonics. So that means the harmonics we have neglected, and only we have taken the fundamental part of the flux density waveform. So that means fundamental means it's a sinusoidal waveform. So therefore, this d curve, this d theta curve is basically coming from this flux distribution, this particular flux distribution. But we have not considered any harmonics, only the fundamental part we have taken. Okay, and if it is like that, and if the flux, maximum flux is phi m rather, then this phi m will vary with time, because the coil is moving or rotating. Okay, and I have explained that if conductor moves or rotates, then the projection under this poles getting changed. So therefore, the net flux linkage to the coil will change. So the flux linkage we had phi theta, which is variable of theta. So phi theta equals to phi m cos theta. And as the theta is coming from this velocity, angular velocity, theta equals to omega t. So we can write phi is basically a function of time for a rotating conductor or rotating coil. Okay, so phi is basically a function of time for a rotating conductor, rotating coil, and that we can write phi t. Phi is a function of t. Okay, so phi is a function of t, which is equals to phi m cos omega t. Okay, so this is how we are getting a variable flux. Otherwise, the initial the flux was only a function of theta. Remember this. Phi is only a function of theta. But this theta we can write in terms of omega, because the conductor is rotating. If conductor doesn't rotate, then this will not appear. Only phi theta will remain. But as the conductor is rotating as a speed of omega, so therefore the phi, the flux linkage, relative flux linkage, that becomes a function of time. And thereby we are getting n d phi dt, and we are getting some finite voltage. Otherwise the voltage will be zero. Okay. So therefore we are getting some voltage Em sine omega t, because the derivative will give another sine waveform. And we are only interested in uh, the the maximum value of that, not the phase angle. And the maximum value, why we are interested? Because we are interested with the DC value. Now DC value is nothing but the average value, as I mentioned. So DC value of anything, any waveform, is nothing but the average value. Just like a purely sinusoidal wave gives us a DC value of 0. A pure sinusoidal wave that is shown in this figure by a black colored waveform is giving a average value of 0. But if we take the rectified waveform, full rectified waveform, then we'll get a finite DC value or average value, and that value comes, for sinusoidal it is 2 Em by pi. So this is the voltage contribution. That is, that this 2 Em by pi is the voltage contribution of only one coil. But in a DC machine, there will be several coils. Now, how will get the net voltage or total voltage in a DC machine? The total voltage in a DC machine will be obtained by adding this voltage. But how to add? That depends on the how the coils are connected. As it is a DC value or average value or a constant value, it's not a phasor. It's not a phasor. It's just a constant value. So we can add normal addition. Okay, so we can add algebraically. But how to add, that we don't know. That depends on the type of the winding in a DC machine. Then we mentioned there are two types of windings available for DC machine. So one is called the lap winding, another is called the wave winding. For wave winding, always the number of parallel circuits will be 2. And for lap winding, always the number of parallel circuits will be equals to the number of poles. That we should remember. So according to that, the minimum number of parallel circuits will be 2. And the minimum number of parallel circuits will give us the maximum induced voltage or total voltage in a DC machine. Because am I audible?
Yes,
Yes,
sir.
sir.
Okay. Any chat? So thereby we try to calculate the total voltage, and the total voltage comes ZA by A Pn phi. So you should remember this expression. This is a very important expression for DC machine. And another form of expression, the same induced voltage also we can write by the constant into phi into omega. So therefore, there are two expressions which are available. So expression number 5 is very important for any kind of numerical problems in a DC machine. JD by A, P, and phi. So don't forget this throughout your course. Okay, so don't forget this. And another expression is K by phi M into omega. It will be required when we derive the expression of the torque in a DC motor. So both the expressions are there. So up to this we discussed in our last class. So we'll start with the construction of DC machine today. So if you have any question, because I have shared the video and many of you have missed some part of the class in the last session. If you have any question or doubt in general, you can ask me, or otherwise I can proceed with the construction of DC machine. Do you have any? Hmm? Anything? Okay. So let us go with the construction. So let me stop that share. Can you see this?
Yes,
Yes,
sir.
sir.
So this is the construction, is a photograph of a construction that I have collected from internet. Uh, so this is almost okay for me. So therefore I have taken this. So there are 4 poles in the first figure which I have explained in the last class was having 2 poles, but this particular DC machine has 4 poles. Okay, as you can see, can you see my mouse pointer?
Yes, sir.
Suppose if this is North Pole, then what will be the next pole? Can you tell me? And what will be the opposite pole? What will be
North opposite pole will be north pole. Next pole will be south pole.
okay? So this will be south and this will be south, isn't it? So that
Yes.
means it completes the magnetic circuit through this, like this. Okay, it will go through the. So this is how it will complete the magnetic circuits. So this magnetic circuit is the most important thing. Without that, any motor or any machine will not function properly. So you have to see the how many magnetic circuits are there. Okay, so these are the 4 magnetic circuits. Okay, so and this inside, as it is mentioned, this is an armature. Armature means the armature is the part of the rotor which holds the armature conductors, which holds the coils. The coils we discussed in the last class. So these coils holds the armature holds these coils. Okay, and armature material, the material is generally silicon steel. I draw something here. Okay, so it's a silicon steel metal. It's a metal lamination. So the made up of silicon steel, and obviously the armature conductors are made up of generally copper. Okay, so there are two types of coil. One is the armature coil, another is the field coil. Here it is written field winding. So field winding also made up of copper, and this is how the field windings are wound. You see, so how many terminals are there for field winding? Because you see, it has started from here. So this is the turns. In which direction?
Counterclockwise.
Okay, so anyway, it's a certain direction. So the same coil, in connected in series with the south pole coil, and the same coil is south connected with the north pole, again south pole, and the final terminal is coming out. So how many terminals are there in the field coil? So how many terminals are there in the field coil? So if you
Two.
start, okay, so 2. So this is one field coil terminal, which is going, and this is returning back. So this is the 2 terminals of field coil. So one is F1, you can write, another is F2. So these are 2 field coils. Okay, so how many armature terminals are there? Armature terminals are also 2. So we call it A1 and A2. So 2 armature coils and 2 field coils basically comes out to the terminal box of the DC machine. Okay, now how the armature coils are wound and how it is connected with the commutator and brush, that I will discuss later. But this commutator is made up of special type of copper that is called hard drawn copper. Hard drawn. I cannot write it here because it's out of this figure. Hard drawn copper. So this is made of hard drawn copper, and brush is made of carbon. Carbon, or it is called the graphite. Okay. So what is the material of yoke and what is the material of pole? Yoke actually holds the, or it acts as a support for the magnetic poles, north pole and south poles. So that means the yoke holds the north pole and south poles, or the magnetic system, the magnetic pole systems. But not only that, yoke also helps to complete the magnetic circuit. Okay, so if the yoke is made up of plastic, then this flux that I have shown here, this flux would not flow through it. So that means yoke must be made up of magnetic material. So that means yoke is also an iron, made up of iron. Okay. So generally it is not laminated, so therefore we use cast steel for it. It may not be laminated, so therefore we use cast steel for it. Why it is not laminated, I will discuss later. But it is generally made up of cast steel, not laminated steel. Silicon steel laminations are used for mostly for the armature core and sometimes for the pole shoes. But the poles are also made up of cast steel, sometimes less silicon steel lamination. So generally it is made up of cast steel, but sometimes silicon steel as well. That depends on the requirement. Okay, so these are the different parts of DC machine from the cross-sectional view. So if you have any doubt, you can ask. Okay, so let me stop this share and just check whether I have any other figure for. Okay, so another view of the DC machine rotor I have. So let us share that. That will give you more clear view of the armature. Okay. Can you see this?
Yes, sir.
Yes, sir.
So this is the armature, and you see these are the laminations. These are the laminations. These are all laminated like this, slice. These are all slice. Okay, and the laminations are hardly zero point 0.4 mm to 0.6 mm thick. Is less than a mm. Okay, and these are the slots. These are the outer portion, so therefore it is very narrow, but inside it is bigger like this. The slots are like this, through which the conductors are passing. So these are the slots. So this is one slot. These are the slots like this. Okay, so through this the conductors are passing. And on these slots, some wedges are there. So therefore you cannot see the slot from the top. Or the winding from the top, because there is some wedge on the conductors or some insulator on the conductor. So therefore the conductors are not visible from the top. But this from this side you can see the conductor, or from this overhang side. So this is called overhang of the conductor. Overhang. Overhang of the conductor. And this part of the conductor is connected with this commutator. So this is called the commutator. Commutator. This is called the commutator, and this is made up of hard-on copper. Okay, so this portion is called the riser. The extended portion of commutator, which is a little bit more height than the commutator, is called the riser, and this is called the shaft. Okay, and these commutators are separated by you see there is some gap. So in this gap you have some insulating material. And what type of insulating material we use there? We use mica. We use mica as a separation between two commutator segments. So these are the commutator segments. So this is one segment, this is two segments, this is three segment, like this. So between two consecutive commutator segments, mica separators are used for insulation, for giving insulation. Okay. Is that clear?
Yes, sir.
Okay. Now, okay. So let me close this, stop this share, and let us go to an animation. I think some animation I already sent you, I think in basic classes. Did I share?
You can find DC motors in many.
Can you see this animation?
Yes, sir.
Okay, you just try to see it carefully. That was
Portable home appliances, automobiles, and types of industrial equipment.
So as I told you, this part is the outside part is the yoke, and the inside portion is the armature, and in between you have poles. So these are the pole windings. So top and bottom, these two windings are the field winding, and inside you have the armature winding. You just try to identify these two windings. So inside the windings are at the center, the windings are armature winding. At the top, at the bottom, the windings are called field winding.
In this video, we will logically understand the.
So this portion is the commutator on which the black thing is mounted. That is called the carbon brush or graphite brush.
Operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible.
So they have started with one coil. As we discussed in the last class, we also started with one coil, but in our coil there was only one turn. So one turn means two conductors, but they have several turns in one conductor, one coil. Okay, so several turns in one coil, but they have taken only one coil. So one coil needs two commutator segments. Just they are showing.
It looks like this.
And these are the brush. Two carbon brushes are required for two commutator segments to take the voltage.
The stator provides a constant magnetic field, and the
So stator provides the constant magnetic field. As I told you, this is a constant with respect to time. Okay, so remember it is constant with respect to time, but not in space.
armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings.
Okay, so as they are saying that that armature will be connected with the with some power supply or DC voltage. So that means they are discussing DC motor here. it's not a DC generator, because they are providing the electric supply to the machine, and they will generate some sort of torque or mechanical motion in the coil. So this type of machine will be called a DC motor, but it's a type of DC machine also.
When the current flows through the coil,
Okay,
an
so
electromagnetic
let me
force
stop
is
this
induced
and
on it according to the
let's
Lorentz.
see whether I have any other video for DC generator or not. Okay. Okay, so I have one more animation. You just try to watch it carefully. Just a minute. I have shared with this sound. Okay. Sound is shared.
Magnetic field.
Here also they have taken only one coil. So one coil means two conductors. Two conductors they are showing by different colors. One by brown, another by black. Okay, so two conductors they have taken, that means one coil they have taken. And for two conductors, again, we need two
The
commutator
conductor
segments.
which can move so as to cut the magnetic flux. Thus, we can say that a DC generator operates on the principle.
Okay, so now the question is, we had a voltage which is purely alternating in nature. So at least if our flux distribution is sinusoidal, we will get a purely sinusoidal voltage. But the question is how this sinusoidal voltage will be converted to a full wave rectified voltage. Because the full wave rectified that you have studied, I think, in some sort of electronic classes. So those circuits are hardly 60 years old. But the technology of DC machine is almost 190 years old. So how then we can have the full wave rectified wave in a DC machine? That is the question. Are you getting what I want to address here? My concern is that we had this purely sinusoidal voltage which is drawn in the black waveform, but out of this we are getting this full wave rectified waveform. So how it is possible to get this full wave rectified waveform from this sinusoidal voltage waveform? So that is my concern. So for that, the arrangement we need is called the brass and commutator arrangement. So that means let us write here that we need, what is our requirement? Requirement is sinusoidal voltage, full wave, that we call full wave rectified voltage, right? Na? Rectified voltage. So how can we get that? So our requirement is it was a sinusoidal voltage, but we need this part will be as it is, but this part will be opposite. So this is our, which we call full wave rectifier voltage, and this is your sinusoidal voltage. Okay. How can we get that? So for that, we don't have any solid state rectifier because the solid state rectifier technologies are hardly 50 to 60 years old. So therefore, what we had 190 years back, that is only brush and commutator arrangement. Brush and commutator arrangement. By this, we can convert a sinusoidal voltage to a full wave rectified voltage. How? Suppose you have a north pole and south pole, and your coil is like this. This is your coil. Okay, is that clear? Now, suppose when whichever part of the coil comes under the north pole will be induced with a certain voltage. It can be plus or minus. Let us take that is plus, that is positive voltage. And whichever conductor will comes under the south pole will get some negative voltage. Okay, is that clear? Now let us draw with this is a brown conductor. This is one conductor. Another conductor, suppose this is a blue conductor. Okay, so that means brown and blue. Now, when this brown conductor comes under the north pole, the positive voltage will be induced. Suppose I have a uh, commutator. They are connected with this, and here I have another commutator part. Okay, so this is one part of the commutator, and this is another part of the commutator. And what we have, this is connected with some brush. So remember, this brush cannot rotate. Only the coil with the commutator can rotate. So that means this part, which I have drawn in color, this can rotate, but the brush cannot rotate. Okay. So suppose this brush is A brush and this brush is B brush. Okay. Now, you just tell me, so what will be the polarity of B brush at this moment and A brush at this moment? What is the polarity of A brush?
Sir, positive, sir. A brush.
So A brush will be positive and B brush will be negative. Okay, so this is suppose one time instant T1. Okay, so that means in the coil also here, if we try to draw it, what type of curve we'll get? So we are discussing where the VAB or brown with respect to blue. Here the brown with respect to blue is positive. So that means we are discussing the positive hub only. In this particular instant which I have taken, so there I have taken the positive hub of the positive hub cycle of the sinusoidal voltage waveform. Is that clear? So there the brown is positive with respect to the blue. Okay, are you getting? But in the next half, these all are rotating in nature. So this is rotating in this way, and this is rotating in this way. So after some time, what will happen? What will happen? The blue will come under the North Pole, and so let me draw it again. That will be, will have more clarity. So let me draw this. After some time, this blue part will come under the North Pole with this commutator, blue commutator, and the brown part will come under the South Pole with this, but this brush will be there. So A brush and B brush will be there. So they will not change their position. So that means AB will be there. Okay. So this is your blue and this is your brown. They change their position. North pole and south poles are same. So therefore, whichever conductor will comes on the North Pole will be positive. And here it will be negative. So that means as the blue with respect to the brown is positive, or brown with respect to the blue. So brown conductor with respect to the blue is negative. So we have to draw it is negative only. So this is the induced voltage. You see, if we look from the coil, then here your brown is positive with respect to blue. So brown is positive. Here your brown is negative with respect to blue. So it's the negative half. Okay. Now you just tell me what about the polarity of A and B brush?
A is positive, B is negative.
So we are dealing with another time instant T2. But again, we are getting the same polarity of these two brushes. That means the brush polarity will not change. So that means if we want to write the polarity for the brush, so that means again it will be like this. If it was like this in the previous instance, so again it will be like this. So this is the polarity of VAB. Okay, so that will come with the terminal. So that will be connected with the terminal. So this is the terminal box. So then the terminal box will get this, not VBRBL, will get VAB, isn't it? So that means if you see from the terminal, then you will see a full wave rectifier there. But if you see from the coil, you will get a sinusoidal voltage wave. Are you getting? Are you getting
Yes,
this
sir.
point? So how the brass and commutator arrangement is acting as a
Sir, can
full
you
wave
repeat
rectifier?
this?
Huh?
Sir, can you repeat this one?
Which part?
This full wave rectified part. How this happens?
Okay. You see in the first diagram, that means when I'm discussing the T1 instant, when I'm discussing the T1 instant, now the question is, the thing is, whichever conductor will come under the North Pole will have positive voltage, and whichever conductor will come from the South Pole will have negative voltage. Okay, so that you have to understand first. First thing you have to understand this. So whichever conductor is coming under North Pole will have positive. That as per the Fleming's right hand rule. Okay. So whichever conductor will comes under the North Pole will be positive, and whichever conductor will comes under the South Pole will get negative. That means for the time instant 1, we are discussing basically the the part, this the positive of the half cycle, positive part of the half cycle. This part we are discussing for 1. Okay, and we can see that you see this brown is positive with respect to the blue. So therefore, we are discussing the positive half of the half cycle, positive half cycle of the sinusoidal waveform. Okay, and there, if you see the polarity of brush capital A and brush capital B, you see this positive is connected with capital A, so capital A will be positive, and the negative blue is connected with the B, so that means capital B will be negative. Is that clear? This question.
Yes, sir.
Now come to the second instant. In the second instant, the blue conductor is now under the under the north pole. So that means here now blue conductor will be induced with the positive voltage, and as the brown conductor is moved to the position at the south pole, so it will have the negative voltage now. So that means here the blue waveform with respect to the brown waveform is positive, or vice versa. The brown waveform with respect to the brown conductor with respect to the blue conductor is negative. So therefore, this is the negative half. So that means we have, if we try to identify which half we are dealing with, so that means this will be the negative half of the coil voltage. So this is the coil voltage. Okay, so this is the coil voltage. This is not the brush voltage. So coil voltage is this. This is also the coil voltage. And this is the brush voltage. Okay, so here the coil voltage is the negative. As the blue is negative with respect to blue is positive, this is negative with respect to the blue. Now here you see the blue is connected with A, but blue is induced with the positive. So that means capital A will be positive. So that means capital A remains positive and capital B remains negative, irrespective of the conductor which is connected with the brush. মানে যে ব্রাশের সাথে যে কন্ডাক্টরই কানেক্টেড থাকুক, এ ব্রাশটা সবসময় পজিটিভ ইনডিউসড হবে, বি ব্রাশটা অলওয়েজ নেগেটিভ ইনডিউসড হবে. So that is the thing you have to understand. The A brush always will be induced with some positive voltage, and B brush always will be induced with some negative voltage. That you have to understand from these two figures. You just try to understand. I will show the animation also.
Sir,
So
does that mean that if the brush commutator arrangement was not there, then our generator would be an AC generator rather than
Correct.
DC generator?
Okay, so again the question is how then you will collect your rotating voltage. That means you see the voltage where you are getting induced, that is rotating in nature, but where you want this voltage, that is static in nature. That means the terminals are static in nature, isn't it? So that means suppose where you are connecting your charger, that is a static in nature, whether it is rotating. তোমরা চার্জারটা যেটা মোবাইলে চার্জারটা যেখানে কানেক্ট করছো সেটা কি মুভ করছে, স্ট্যাটিক রয়েছে?
Yes, sir.
It's a static.
Yes.
Because the static thing can be connected. So that means the terminal should be static. Any machine should have its terminal static. But the voltage where which we are getting induced in the machine, that is rotating in nature. So that means you have to understand very clearly that we should have some sort of interface between the rotating and static. So this is one arrangement. The brush and commutator is another arrangement which gives us a rotating to static interface. And এটা তো একটা করেই যে it converts AC to DC. That is one objective. So another
Yes.
objective of brass and commutator arrangement is it also act as an interface between a rotating reference frame and static reference frame. It acts
Yes.
as a reference,
Yes.
interface. Okay, so that means if you want the voltage, just the voltage which is induced in the coil, that means you want the coil voltage directly. You don't
Yes.
want to rectify it. That is your objective, so far I have understood.
Yes.
Isn't it? So for that, you need another arrangement, another type of interface, which will make the interface between the rotating and static reference, but it will not convert, it will not make any conversion. বুঝতে পারছো আমি কি বলছি?
Yes, sir.
তুমি
Yes,
যেটা
sir.
চাও
Yes, sir.
সেটা কি করবে, রোটেটিং থেকে স্ট্যাটিকে নিয়ে আসবে, কিন্তু কোনো রকম
কিন্তু-
কনভার্সন করবে না।
ঠিক স্যার, ঠিক স্যার।
So those type of arrangement is called the slip ring arrangement. Okay, so that means what we need for that, if you as you have asked, so I have to answer that. Let me check whether I'm getting any chat. Okay, slip rings. So what is slip ring? Slip ring means, suppose I have this coil. Okay, so maybe one with brown, another with blue. The same thing I'm drawing, which is shown in the video. Okay. And what we need, why we need, okay, so we need some ring. This is one ring. Okay. Again, we need the brush. Without the brush, it is not possible to make this interface, because graphite used having some lubrication property. So this is how you can create. So these two rings are complete rings. These are not splitted rings. These two are complete rings. So one complete ring will be connected with the blue conductor. Another complete ring will be connected with the brown conductor. Okay, so that means the conductor, blue conductor is always connected with the blue slip ring, and the brown conductor is always connected with the brown slip ring. So they will not leave each other. And there is no connection between this blue slip ring and the brown slip ring. There is no connection, no electrical connection. So that means if this is A and this is B, now if this is positive and this is negative, so that means when this, suppose this is your T2, when this A is positive, and what about the B? B is negative. Okay, but when this brown conductor will be positive, that means A1, when the so that means B is depends fully on the brown. This B, capital B, is fully depends on the brown. So then the B will be positive and this will be negative. So you see the brush polarity are varying in time. So as the brush polarity is varying in time, that means the brush voltage VAB will get sinusoidal. Okay.
Okay, sir.
So this is called the slip ring arrangement. So let us go back to this video.
Discuss how a DC generator operates. Consider a simple loop generator. Let's rotate its single-turn rectangular coil, say ABCD, about its axis in the magnetic field.
So in the second figure, they have used two slip rings and separated each other, completely separated from each other. You see, two slip rings, and these slip rings are connected with a brush, and the brush terminals are connected with some multimeter. There they're trying to see what is the waveform of the voltage. But we'll get alternating voltage in
Note
this
that
case.
both the permanent magnet and electromagnet can be used to produce the required magnetic field. We see that as the position of the rotating coil changes in the magnetic field, flux linked with it also changes. Thus, an EMF is induced in the coil in accordance with the Faraday's laws of electromagnetic induction. This induced EMF is proportional to the rate of change of the linked magnetic flux. We also see that after every half rotation, the sides AB and CD of the loop swap their positions. Thus, the direction of current flowing through them gets reversed. Such a current undergoing periodic directional reversal is known as alternating current. To split rings are used. Unidirectional DC current. Split rings are used. These split rings are made of a conducting cylinder which is cut into two halves or segments insulated from each other by a thin sheet of some insulating material like mica. The ring segments are also kept insulated from the central shaft and are connected to the ends of the coil and the carbon brushes. Now let's discuss how these split rings change the bidirectional alternating current into unidirectional DC current. Let's assume that current is flowing along ABCD. We see that brush 1 is in contact with segment A. Which acts as the positive end of supply. And brush 2 is in contact with segment B. Which acts as the negative end of supply. Therefore, the direction of current in the load resistance is from M to L. Now, after half revolution, direction of the induced current in the coil reverses and it begins to flow along DCBA. Also, position of the segments A and B gets reversed and brush 1 comes in contact with segment B. Which now acts as the positive supply. And brush 2 comes in contact with segment A. Which now acts as the negative supply. Thus, we see that the direction of current in the load resistance still remains to be from M to L. We also see that the position of the brushes is so arranged that the changeover of segments A and B from one brush to the other takes place when the plane of rotating coil is perpendicular to the plane of magnetic flux. When EMF induced in the coil is zero.
So have you understood this? So they are discussing about some current, but if there is no current also, the voltage waveform will get fully rectified. The DC generator may not be connected with any load. The DC generator may run at perfectly no load, but still the voltage waveform will get full of rectified waveform. Okay, so that is the thing. So let us go back to our discussion. So if you have any question, you can ask me. No question? Suppose I am drawing the coil voltage, which is for one coil and after full wave rectification. So can you tell me, as there are several coils in a DC machine, so if this coil, suppose, let me draw this, suppose this is the coil system, and suppose this is the coil which we have drawn. So this is your A prime coil. There will be another coil which will be here, another coil will be here. So this is how there are several coils. So this can be B prime, C prime, D prime, like this. So this is the center. So this is how, and this coils are rotating at a speed of omega. Okay. Now, if I have drawn it for A prime, can you tell me what will be the voltage in B prime coil?
Sir, the voltage should be the waveform should be similar, but it should lag the voltage of the EAA prime. The EBB prime will lag the voltage EAA prime.
So I wanted to.
We saying the previous one. We saying this.
Sir, I am Swarnadeep Saha.
Swarnadeep Shah. Anybody else? Anybody else want to say something? I can see many of you there in the class. So Vinay Kumar Rajak, are you there?
Yes, sir.
Can you tell me that what should be the voltage of this coil B prime?
Sir, the magnitude will be same, but as Swarnadeep said, that it will lag the voltage A prime.
Why it will lag?
Because, sir, it is producing same amount of voltage.
And that is same. That I agree with you. First thing, that means the magnitude will be same, but you are saying it will be lagged behind from this A prime coil.
Sir, because it is rotating in anti-clockwise direction.
And
So it will attain peak peak voltage at a later stage than AA prime.
Who is saying this?
So Debanjan.
Okay. Anybody else? Roof lekha Rai?
Yes, sir.
Can you say something in details why it is lagging behind this coil AA prime voltage? It's very simple logic.
Because sir, as it is rotating in anti-clockwise direction, the maximum flux for the coil B will be sometime after, like, the maximum flux will pass through the coil B sometime after the maximum flux is passing through the coil A. Therefore, for B, it will attain maximum voltage at some later stage after.
Can you tell me what will be the angle? What will be the angle of this lagging?
It will depend on the number of coils. So,
Anything else?
if the total number
Of coil from this figure, can you tell me what will be the angle?
Omega t.
Omega t. What is the value of t? Because t is a completely variable.
Sir, the angle between A and B. If the center is O, then the angle AOB will be
Who is
the
saying
angle.
this?
Sir, Pushpal Banerjee.
Let me draw this. You just tell me whether it is correct. So Pushpal is saying if this is O, isn't it?
Yes, sir.
If this is O, it's difficult to draw straight lines.
So BB dash will lag AA dash by 30 degree.
Not 30
BB
degree.
dash will lag AA dash by 30 degree.
So this is the angle, isn't it? Pushpal?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
So this
I
angle is called the angular slot pitch or gamma. Okay, so between two slots, it depends on the angle between two consecutive slots. That is called the angular slot pitch. Okay, so it depends on that.
So please write the term.
Huh?
So please write the term angular.
Angular slot pitch, but the thing why I am not writing it, because the angular slot pitch will be measured in electrical angles. Okay, anyway, I am writing as you asked me to write. So gamma is called the angular slot pitch. But in electrical degrees. Electrical degrees. Expressed in electrical degrees. Okay, so I think you have understood a little bit why we are getting this lag. So that means the next voltage will get I'm trying to draw, but in this type of board it is very difficult to draw, but still I am trying. But if you have your notebook, you just try to draw well, better than me, I think. So this is how we'll get the voltages, isn't it? And everywhere you will have this gamma angle. This gamma angle. Okay. Now, suppose you have these three coils. Then what will be the voltage? The voltage will be the superimposition of all these voltages. So that means it will be before this will be there. Before this also this will be there. So superposition of these all these voltages. That means If we make sum of all the coil voltage contribution, the coil voltage will be like this. So this is the net voltage here. Let us write small EF because it's the time varying thing. So EF, which gives your actual net voltage EF. Are you getting? Let's see what is the chat I am getting. VBB will lag VA by gamma. And VCC will again lag VBB by gamma. And VAA by 2 gamma. So that I have drawn in the figure. And if we write all this, if we draw all these coil voltages and if we make the sum, I will get just like this black waveform, which will have very small ripple. You see, ripples are very less. Okay. So that means the story of almost 190 years back, then neither we had any rectifier nor we have any kind of filter. Okay, so without any rectifier, solid state rectifier or any filter, we can make the thing unidirectional or DC, as well as we can also make the thing ripple free, which is the job of a filter. Are you getting? So this is the technology of a DC machine. So you are getting almost ripple free DC. Okay. Anando Chakraborty raised his hand. Anando, do you have any question to me?
No, sir, it was by mistake, sir.
Okay,
Sorry.
understood. Okay, thank you. Any other question? Have you understood this point? So how we are getting this voltage? Okay, but if we want to add this a similar way, if we are only you don't interested with the waveform, only we interested in the magnitude, then whatever we did in the last class that we can do. So that means C by A into E average. Isn't it? So that we did now in the last class. If we are interested only with the values, not in the waveform nature, then directly we can add like this, because it's a DC value. It's just a number. It's just a constant number. It's not a vector. It's not a phasor. Remember, if we are dealing with some AC machine, okay, where we have all these voltages, but with the negative half as well. So this will have some negative half. This will have some negative half. This will have some negative half. Then the thing will be more complicated, because there you cannot make the algebraic summation. All these sinusoidal, there will have to be represented by some phasors, and phasors cannot be add like this. There is a formula for phasor summation, phasor additions. Okay, so there the thing will be more complicated. But for DC machine, the thing is easier, because we are concerned only with the average voltage or the DC voltage. And DC voltage is just a number. So therefore, when we are calculating the average, the total voltage from the machine, then we can just add the coil voltages. So that is the advantage for DC machine. For AC machine, we have to add all these voltages vectorically. Remember, when you will study the synchronous machine, which is called the AC generator, there you have to add all these voltages vectorically. This algebraic addition will not be valid for those machines which generates alternating voltages. Here we are only interested with the DC voltage from this DC generator. So therefore algebraic addition is sufficient. Have you got this point? Okay. Now today time is not there, so only a small thing which I have skipped in the last class I will discuss. That is the difference between the electrical angle and the mechanical angle. Okay. So that I will discuss. Then we will close the class for today. Now you just see, if I ask you to draw the distribution, if you ask you to draw the distribution, can you draw this distribution for a DC machine 2-pole sinusoidal distribution? Can you draw it? You just try to draw. I will ask you randomly and show. You have to show. You just draw it quickly. Randomly, I will ask you to show. Have you drawn? Debraj Banerjee.
Yes, sir.
You just show your graph. You have the notebook.
Yes, sir.
You have the notebook with you.
Yes.
You just switch on your video and you just show me. Just a minute. I think everybody will see you. Okay,
Sir,
you just
got
rotate
it,
it.
but I
You just rotate
got
it.
it. Which one?
Okay, তুমি এতে বলছো নাকি মোবাইলে ধরেছো সেই জন্য এরকম লাগছে। Okay, so you just tell me what is the bottom portion or the negative portion?
Here, if we draw it, it would be the B point or it will be the C point.
No, I want to know that what is the north pole and what is the south pole.
For North Pole, it would be somewhere like here, North Pole. And South
Therefore,
Pole
for
would be
north pole you have
here.
drawn negative because north pole generates the negative, isn't it?
Yes,
But
by
what is the
potential,
extended portion that I have not understood?
the extended portion, because here at the origin, here I assumed it to be the point A, and A and no,
Okay,
sorry,
I
it
want
will
to
be
ask
the
that what is this portion? What is the after 360 degree? What is that? That I haven't understood. After
this
360
portion.
degree, ওই লাইনটা কেন এক্সটেন্ড হয়ে গেছে কেন? এটা তো দুটোই পোল আছে। Anybody
Yes,
want to show me?
but
Anybody else?
so can I stop screen record?
You can stop it. You can stop your video, then it will off. Okay, so anybody else? আর কেউ করনি? করতে পারছো না? নির্মাল্য নন্দী? Are you there? নির্মাল্য নন্দী? It's not there. Paulomi Das.
হ্যালো হ্যালো
Nirmallo Nandi.
হ্যালো স্যার
Bolo. So can you
Yes,
have you
sir.
drawn? If you have
Sir.
drawn, you just switch off on your video and show me what you have drawn.
শিওর স্যার জাস্ট a minute sir. So this one.
Not coming. You don't have to share. You just switch on the video. I'm not getting it. Your video and audios are off. Okay, so next I will ask Paulomi Das.
Yes, sir.
Have you drawn?
Yes, sir.
You just switch on your video and show me.
Sir, is it visible?
Yes. North pole, south pole, correct. Correct. Now, again, I will ask you to show that if there are 4 poles, then what will happen?
Okay, sir.
I think you all have seen that what Paulomi has drawn. That is the correct one. But now I am asking you, if we have 4 poles instead of 2 poles. In the same figure you have to draw, remember, in the same figure, not in a different figure. In the same figure you have to draw it for 4 poles. Quickly. Randomly I will ask you. So let me take the attendance then. It's droid. I'm just taking the attendance. Okay. Attendance is over.
Sir, you told me to remind one thing of the previous class. You told me to remind you in the next class.
Regarding what?
Sir, in the previous class that I asked you that you told that when the North Pole is in the stator, then we consider negative flask, and when it is in the rotor, we consider positive flask. I asked you that why it is different for stators and rotors, and you told
Actually,
that,
I didn't find that that is basically referred as a convention in each book, but I have not find any reason for that. But the reason may be if you have both the conventions are same for rotor and stator, then when you will draw the two waveforms and you will try to actually the effects are different. Okay, for stator and rotor, because sometimes in the stator you have the armature, in the rotor you have the field. Here the thing is different. Here in the stator you have the field and the rotor you have the armature. That can be different. So if you have the similar convention, then it may be confused. I think due to that only it has assumed like it has like this convention.
Okay, sir. Thank you, sir.
Okay. Shashwat Mukherjee.
Sir, excuse me, sir.
Anybody?
Sir, Debanjan sir. Sir, I came across a convention regarding, I think it's related to this. It said that if the flux lines are moving away from a point, then the point is taken to be positive. The flux at the point is taken to be positive. And if the flux lines are moving towards a point, then it's taken to be negative. So would that work?
But is that related to North Pole and South Pole? Why it is?
Yes, in a rotor, basically, if the point is say towards the North Pole, then the flux lines are arriving at the point from the North Pole, and then they are moving away from the points towards the South Pole. So if the point is more towards the North Pole, then it's assumed that the flux line is moving away from the point towards the South Pole, and therefore the flux is taken positive.
Okay. Okay, so it may be one reason. Okay, so let me see. I will if I get some better answer, better logic, I will definitely discuss in this class. Okay, so I have asked Shashwat Mukherjee to show your waveform. Have you drawn something? Shashwat, are you there?
Yes, sir. I'm opening the pen. Will it be like this?
Yes.
Is it visible?
Yes. So that means here how many negative? You have two negative, na? So that means in same 360 degree, you have taken same 360 degree, isn't it? The total space you have taken the same.
Yes, sir. I have taken the same.
So that means what he has drawn. I am just taking the sinusoidal for easier to draw it. So previously it was North Pole and this was South Pole. The Ptolemy has drawn, and now whatever Shashwat has drawn is like this. The amplitude may be different, but thing is like this, isn't it? Okay.
Sir, the amplitude will be same or different?
Yes, amplitude depends on the strength of the pole. You can use the same. So the amplitude depends on the strength of the field. That means in case of electromagnetic field, the number of turns and the amount of current flowing through it. সেটা তো মানে সেম হতেই পারে বা ডিফারেন্ট হতে পারে, সেটা আলাদা ব্যাপার। But here you have বলো,
amplitude does not depend on the number of poles.
No,
so
no.
It can be same for both.
It can be same for both.
Okay.
It can be same for both.
If the other factors are constant.
If other parameters are constant, it will be exactly same. So this 360 degree, within this 360 degree means total circular space is basically how much? It's a 360 degree only, isn't it? Total complete rotation means 360-degree rotation. This 360 degree is basically your mechanical angle. Okay. Now, as per the waveform is constant. For waveform, for 2-pole, we have this is 360 degree. But for 4-pole, so this is for 2-pole. But 4-pole, our 360 degree moves to here. Isn't it? So that means here our 720 degree for 4-pole. Okay. So these are basically the electrical angles. So electrical angles which we get from this flux waveform or current waveform. Okay. So that is basically our electrical angles. So that means for 4-pole, okay, let us start with the 2-pole. For 2-pole, electrical theta equals to mechanical theta. For 4-pole, electrical theta equals to what?
So 2 into mechanical.
Correct. 2 into mechanical theta. So that means in general what we can write. So electrical theta equals to P by 2 into mechanical theta. So electrical angle is P by 2. That means electrical angle depends on the number of poles. Okay, are you getting? So this is the conversion. Okay, so today already the time is over, so I have to stop here and I will discuss how we are getting this expression from this. Actually, we want to explain this. F equals to Pn by 2. In the next class, I will discuss this. Okay? Is that clear? Anything else for today?